everybody finds. This pattern is so typical across so many different systems. These are two graphs from my work where we're basically finding directional selection for earlier reproduction in two different gardens. But this pattern is so consistent. There have been reviews written about why do we not see stabilizing selection? Why are we seeing directional selection for earlier flowering? And in this system, our local genotypes, which are here in yellow, they're flowering 10 to 15 days later than the optimal timing of reproduction. So there's something weird going on with reproduction. But we also know that plants are flowering earlier in response to climate change. So many years ago, I was talking to David Inouye at the Rocky Mountain Biological Lab, and he said, "Hey Jill, I have some data on Boechera, do you want it?" And I said, "Hey David, yeah." That's all I said. And so we've been working with some of David's data where he's been collecting information on the timing of flowering of Boechera and a bunch of other native species every other day in plots that he's arrayed across alpine meadows and subalpine meadows, actually, more subalpine than alpine. But he's been collecting those data since 1973. And what you can see with Boechera, here's the ordinal date of flowering and year. Boechera has been advancing its flowering time by 3.7 days per decade. And anytime you work on one species, people always say, "Yeah, but how does that generalize to other species?" And so I will say it generalizes really well. So these are 5 other species of flowers that flower in the spring, and they're all advancing their phenology at almost the same exact rate. So they're all responding potentially to different cues or potentially to the same cue, but we're seeing these phenological shifts that are quantitatively similar, not just in Boechera stricta, but across a diversity of species here and in other locations. And we're seeing these phenological shifts in a diversity of organisms outside of plants. So spring flowering species are reproducing earlier and at a lower heat zone. So we said, well, why? Can we identify any of the drivers that are potentially influencing this earlier reproduction? And what we find is that there's this really nice correlation between the timing of snowmelt and the timing of flowering. So timing of snowmelt on the x-axis, timing of flowering here. Boechera stricta advances its timing of flowering by about half a day for every day change in snowmelt. And the other species are doing things that are almost exactly identical. But it's a correlation. Who knows if snowmelt timing is actually driving this? We actually know that snowmelt is driving this, at least in Boechera. So again, like 10 years ago, Zach Giesen, who was a PhD student at that point, had been doing all these snow removal experiments, and Zach said, "Hey Jill, I have some data on Boechera, do you want it?" I was like, "Yeah." When would you say no to that? So Zach had been doing these snow removals, and this is basically just showing that he found a significant acceleration in flowering time in his snow removal treatment. His snow removal actually accelerated accelerated snowmelt by about 17 days. And we would predict a 5 to 10 day acceleration in flowering time, and that's basically exactly what we found. So the prediction from these long-term flowering time records that David Inouye has been keeping since the mid-1970s map on really well to this experimental result. So this 17-day advancement in snowmelt resulted in about a week acceleration in flowering. And this tells us that snowmelt timing is a really important driver of flowering time in the system. But in addition, it tells us that we can do these experiments where we basically just remove snow, and that's a really good manipulation of climate change. So I've been doing that for a decade or so. This is almost 8,000 records of flowering over that time frame. And we can plot this out in perhaps the most boring way possible, right? Flowering time is a function of the garden, and you can see in all garden sites, snow removal advances the timing of flowering. But this doesn't actually give us very much information about the driver. So instead of doing that, we can actually correlate the timing of flowering with the timing of snowmelt across this entire data set. And that's what I'm going to do in a second. We're going to look at flowering phenology as a function of the timing of snowmelt. And if plants can perfectly track climate change, or if plants can perfectly track snowmelt timing, the slope of this should be 1. Remember that the slope from David Inouye's data was about 0.53. If flowering is delayed when there's accelerated snowmelt, the slope will be negative, and if flowering is accelerated, the slope will be positive. The reason this is important is that we know that phenology is changing with climate change, but we don't really understand the drivers, and we don't really understand the extent to which populations are tracking these phenological or these shifting climatic factors. So in the context of climate change, you could see a situation, so this is the historical relationship between the phenology of the organism and the environment from a paper by Amy Eiler and her colleagues. And in some cases, maybe the population is tracking the environmental shift perfectly, right? They're moving in the same direction at the same rate, and that might suggest that these populations have some capacity to adjust their phenology in response to climate change in an adaptive way. You can also see a scenario where the environment changes, but the phenology doesn't. So basically the environment is we're like pulling the environmental rug out from under these locally adapted populations. And finally, we could see that there's imperfect tracking. I mean, there are obviously more options than this, but phenology may shift slower than the environment. The environment may shift at a faster rate. So what's really cool in this system is the patterns that we found. So these are color-coded by the garden, with the garden elevation over here. This is in ambient snowmelt, and this is in snow removal. I haven't shown you the actual predictions. Here they are. So this is just to show you this is highly significant. When I first saw this, I was stunned. This is really cool. Remember I told you that in natural populations in David Inouye's records, the slope is about 0.53. We only see that at the highest elevation garden. And instead, what we see in these lower sites is there's actually this super weird negative relationship, which I did not predict, did not expect, and don't totally understand yet. But this suggests that earlier snowmelt actually delays flowering. So the questions that I have is, I would wonder whether the constraints on plastic responses may be larger in the harsh environments at low elevation, or it's possible that maybe delayed phenology could be advantageous there. So it could be advantageous here. So I'm going to leave those questions up. And I don't have an answer to those questions yet with flowering time, but I do with germination timing, because we see the same pattern. Now you might be saying to me, Jill, where's your data from the higher elevation gardens? It is so hard to get up to them at the beginning of the season. I'm like literally walking for 4 hours to get there over snow, uphill both ways. I'm not joking, it's uphill both ways over snow. Because I have to go up and over a mountain pass. So I don't have great germination phenology data from those higher elevation sites, but you'll notice that at this lower elevation site, we see that negative relationship again. And I'm just going to change this a little bit. This is the ordinal timing of germination, the ordinal day of year. We can also calculate germination phenology as the number of days that elapse between snowmelt and the timing of germination. And you see when you do that there's this negative relationship everywhere. So in every site, these early snowmelt days are actually delaying they're delaying germination. But what I have done here that I haven't done with flowering time yet is link this to fitness. So I've actually asked, how do these phenological patterns link up to the survival outcomes of the seeds that have germinated? So we get the timing of germination of the seeds, and then at the end of the season we know which of those seedlings have survived the whole season. And so here are the fitness consequences. They're in these contour maps, which is basically like reading a topographic map. Yellow is higher. So this is the lowest elevation garden. This is timing of snowmelt versus germination phenology. And what we're finding here is that delayed snowmelt is adaptive only or favored only under, delayed snowmelt, delayed germination, it's like 10, almost 11 o'clock my body time, so my brain is not totally here, so I'm sorry. Delayed germination is favored only under delayed snowmelt. So there's something weird going on with these delayed germinants under really early snowmelt. This is the pattern from the second garden. So you see that you can have higher survival of seedlings under both early and late, early and late of germination, but only when snowmelt is delayed. And then there's this weird pattern in the middle. This is the pattern that makes the most sense to me biologically. Here what we're seeing is that delayed germination is advantageous under early snowmelt, and rapid germination is advantageous under delayed snowmelt. That makes so much biological sense to me, because under delayed snowmelt it might be better to germinate early, then you'll have a longer period of the growing season to live. So this is where I'm heading with the flowering phenology data, although I haven't quite gotten there yet. Okay, so just to wrap this up, I want to tell you about one more experiment that we have done. So snowmelt timing is this really complex environmental variable, and there are a lot of environmental drivers that could actually be happening underneath the hood with snowmelt timing. So snowmelt timing actually can tell you a little bit about when the season starts, but it can also tell you about drought stress. So oftentimes early snowmelt enhances drought stress. It can tell you about how much temperature or heat an individual will experience across its lifespan. So this is growing degree days as a function of timing of snowmelt. So with delayed snowmelt, you actually get lower growing degree days across the season. And this is mostly because in these higher elevation sites, snowfall starts so early. But there's another thing that I hinted at earlier, and that's frosts. So spring frosts are really prevalent at low elevations, and I made this on the airplane and the font is really low, and I'm really sorry about that. But the y-axis here is air temperature in degrees Celsius. So these two here are the lowest elevation garden, and then this is the second garden. And this basically, we're looking at fluctuations in air temperature over time. This is in 2021, this is in 2022. But what you see, oh, here, I need to show you this. This is the current snowmelt timing of all of these locations. So after snowmelt, there are these really prominent freeze-thaw cycles that plants experience in both of these locations across both of these years. So they're getting into this frozen territory even after snowmelt. This is the projected snowmelt. It's really hard to know how much freezing plants will be exposed to in the future, but there is some suggestion that these freeze-thaw cycles in some locations could become more prominent. So you see multiple freeze-thaw cycles after snowmelt in current climates in the low elevation sites, and basically none in our higher elevation sites. So even in this mid-elevation garden, there's very few episodes of freezing after snowmelt, and you see basically none. And that's because by the time snow melts out here in early July, it's just not going to be cold at night. So we actually did a growth chamber experiment to look to see whether there's evidence for geographic or genetic variation that is associated with this geographic climb in freezing tolerance. And before I do that, I should mention that Ian Breckheimer is a collaborator who's done a lot of the climate modeling for us. So here we're looking at accumulated freezing degree days in the month after snowmelt. If you don't know what freezing degree days are, think about growing degree days. Growing degree days is heat accumulated above some threshold. Freezing degree days are basically the reverse. It's the number of days below a certain threshold, and we set that threshold here to be, I think, 0 degrees. But you see a lot of these frosts in low elevations, and basically no frosts once you get into those high elevation locations. So my former grad student, Anam, teamed up with me and an undergrad in the lab, and we basically took these freezing chambers. They're really cool. You can freeze plants, super fun. So we looked at the germination success of seeds exposed to control conditions, and then Anam created 3 different treatments that reflect climate change to a certain extent. So he took the data from the lowest elevation site, said what's the average coldest night after snowmelt, and then what's the average coldest night, oh wait, yeah, this should be, okay, this is average coldest night after snowmelt, coldest night, I think this is getting to before snowmelt. This is average, this is coldest. Okay, average night after snowmelt, I'm so sorry. Coldest night after snowmelt, coldest night before snowmelt. We put a ton of seeds from across this elevational gradient with the prediction that low elevation genotypes would be the most tolerant of freezing cycles. And that's in fact what we found. Basically, there's no relationship between germination success and elevation in our control treatment. That looks positive, it's actually nothing. There's no relationship here, but in these 2 really pronounced cold environments, you see that low elevation genotypes have the greatest fitness. And we only subjected these plants to 1 episode of freezing, so one might imagine that multiple episodes of freezing would actually further exacerbate this pattern or make this pattern even clearer. We also did this we looked at relative growth rate. Again, no pattern in the control or this more benign freezing environment. You see the same negative pattern down here, and you might be saying what's going on there. Oh, I didn't show you. Okay, it's because all of these guys died. So we couldn't measure growth rate because all of the seeds in all the seedlings in this treatment died. We also find that seed dormancy rates vary with treatment. So we subjected seeds to these various different treatments, not just the seedlings. And then we categorized them as to whether they germinated, whether they were viable, or whether they were dead. And you see that in this most severe treatment, a much larger proportion of the seeds ended up dying than in these more benign treatments. So all of that together suggests that there are these really interesting drivers of fitness in this system, but in other systems as well. And it may not be the classic drivers that we think about when we think about climate change. It's somewhat unusual to think of climate change as potentially increasing the risk of frost damage to plants. But that is one of the elements that's come from this. So basically, in this part, we're finding that plants are accelerating their flowering time, that they're imperfectly tracking these changes, and what I really want to know is whether these negative norms of reaction or this negative plasticity could be adaptive, and then do some follow-up work actually trying to understand whether we can identify loci through approaches like genome-wide association studies that are associated with plasticity in this trait. The fitness landscape is really cool. It depends on both phenology and the environment. So you can't simply monitor fitness and selection on its own. And then freezing temperatures could potentially constrain phenological shifts. So more generally, what we find is that there's strong evidence of local adaptation. It varies across the landscape and across an ontogeny life history. Climate change could shift fitness landscapes and disrupt long-standing patterns of local adaptation. There's strong evidence that there is limited opportunity for evolutionary rescue from standing genetic variation. So genotypic variance and climate tolerance declines under projected climates. And our models do project really large-scale contractions of populations, but that could be minimized through approaches like assisted gene flow. But then, as we'll be talking about tomorrow, there's so many complications when it comes to assisted gene flow of deciding where to move seeds, when to move them, how far to move them. But I was going to move this. But anyway, this is my ORCC grant. I just wanted to show you. We're not ready for prime time in terms of sharing, but we've been working on Chamaecrista fasciculata, which is a nitrogen-fixing legume. And our goal in our grant is to try to use different modeling approaches to project populations growth rates and distributions going into the future, from really simplistic species distribution models to genetic offsets and more complex quantitative genetic approaches, and basically ask how much data do you actually need to make good projections going forward. Oh, that was also Lily, sorry. Jay knows Lily, but anyway, Lily's been involved with this too. Anyway, this was a late presentation for me to give. I'm probably not enough sleep, so I apologize for stumbling a couple of times, but that's what we're up to, and I'm happy to chat with people at any point.